day, everybody. Once again, we're back together. I hope that you are not stressing, around the exam. And as you continue with the other exams, please just remember, focus, make sure that you do the best that you can. All right. So we're going to be looking at question 5 on the DBE November 2021 paper. Okay, if you haven't subscribed, please just be part of the family. And of course, for those of you who need assistance with mathematics or physical science, you can get in contact with me. All right, our email address is info@mlungisinkosi.co.za. All right, so this is based on work energy principles. Okay, or I should say energy principles, work energy and power. All right, so let's look at the question. They say we've got a 2 kg box which is released from rest. See, I like that because it also tells us that our initial velocity there should be 0. Okay, they say 5 meters above the ground. It slides down the smooth, frictionless, curved track PQ. Right, now please, I want us to note that they told us that this track is frictionless. Okay, so there's no applied force, there's no frictional force. They say it slides down a smooth, frictionless track. Okay, right, now they say state the principle of conservation of mechanical energy in words. Okay, whenever they say that, please remember that there's a very high likelihood that you would have to actually use it in the next question. Right, remember it says in an isolated system, okay, the total mechanical energy remains the same, okay, or you can say is conserved in that case. All right, now going to the next question. They say use principles of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. Okay, so in this case, we want to know what would be the speed when we reach point Q. So we can use the principles of mechanical energy. So we can say, well, it means that Emech, okay, so remember that's 5.2. Okay, so we can say Emech at P should be equal to Emech. Okay, all right. So Emech at Q, right? But when we look at P, so if we say EK plus EP, potential energy at P should be equal to EK plus EP at Q. So in this case, remember our initial velocity at P is 0. So it means that our kinetic energy at P is 0. Okay, plus our vertical potential energy, all right, gravitational potential energy, I should say, mgh at P. So there is potential energy there because it's actually elevated in space. Okay, so from the ground there, it is actually elevated 5 meters. So kinetic energy, so we want the velocity when it gets to point Q. Okay, so that's half mv squared. But what's the potential energy when we get to Q? Of course, in this case, we've reached, the place of 0 potential because the height is 0 there. So in that case, it means that becomes 0. And by the way, I think you've seen me do this in the past because you're talking about the same thing. We can divide both sides by m. Okay, so even if they had not given us that mass there, okay, if you want to, you can substitute for that mass. Okay, for the skeptics, let me just substitute that mass there. So that's going to be 2 times 9.8 times the height, which is 5. I'm just doing that so that in future you remember. I remember there was a question where they did not give the mass of the object, and if you didn't know this trick that you can actually divide by masses, by the mass rather, you wouldn't have been able to solve that question. Okay, so that's half of 2 times v squared. Okay, and we'll basically just do our gymnastics here. Half of 2 is 1. Okay, and you take the product, then you just take the square root. So in this case, it's just simply going to be the square root of 2 times 9.8 times 5. Okay, I get a speed of 9. Okay, I think I might as well say just 9.9 meters per second. Okay, it's 9.899, so yeah, I rounded that off to 9.9 meters per second. That is. Okay, right, now let's go to the next question. Now they say the box passes point Q, all right, and remember at point Q it's moving at that speed there, and moves to a rough horizontal surface. So they are telling us this surface here is rough, okay, before striking a barrier at point R at a speed of 4 meters per second. So we know here the speed is 4 meters per second, and we know the initial speed there was 9.9. Okay, and they say to us, when we know the distance is 10 meters, okay, they say use energy principles to calculate the magnitude of the average frictional force acting on the box as it moves from Q to R. Now, I want you to please note, in this case, we can use the work energy theorem, okay? So, if you note there, right, what would be the work, or rather, which force would be acting on the, on this box, as it moves, right? So there are actually only 3 forces. It would be the frictional force. Remember, there's nothing pushing the box, and frictional force is opposing motion. It would be gravitational force, and it would be the normal force, right? So in that case, horizontally though, the only force acting would be the frictional force. So we can say, well, the net work done is equal to the change in kinetic energy. But if we look at net work done, in this case, it's going to be F net. Okay, remember we're looking for the force, and that's why I'm going this direction. F net delta x, the cos of the angle, angle theta. And for those of you who find this confusing, it simply means you haven't watched our our series, or rather our playlist on work, energy and power. Please go and empower yourself with that one. I make it quite simple. Okay, right, so this would be kinetic energy final minus kinetic energy initial, and I'm doing this because I'm also mindful, that would be final minus initial. I'm doing this because I know they've already given me both the velocities. I do have the velocity at R, and I have the velocity at Q, right? Now, what would be our net force, right? I'm sure you get this by now. So this would be the frictional force, and that's what we're looking for, right? So our frictional force, what would be the displacement? Our displacement would be 10, okay? And in this case, our angle, remember we ask ourselves, what's that angle between direction of motion and the force in question? Okay, so here's the direction of motion, here's the force. What's the angle between them? It's 180. So in this case, that's 180. And our final kinetic energy, this would be half. The mass is 2. Final velocity, we said it's 4. Remember, don't forget to square that. Minus a half, our mass is 2, and our initial kinetic energy, which is at Q, was 9.9. Remember to square that as well. Okay, right, so all we need to do now, so this becomes 10 times cos of 180, that's minus 10. So this is minus 10 times the frictional force, and what we need to do is just find the product that side, and I get it's minus 82 8.01. Okay, and in this case we're going to obviously divide that by -10 on both sides. Okay, and I get a value of, so this is going to be actually 8.20. Okay, newtons. So it means that our frictional force is going to be 8.2 newtons. Okay, and I'm certain some of you are going to ask, wonder, but why did the frictional force come out as positive there? Remember, what we did was to calculate the magnitude of it. Okay, already the cos of 180 had already told us that it's actually going in the opposite direction from the motion. Okay, so what we did get here is just simply the magnitude of it. Okay, so please don't worry too much about that, and please remember, they did say the magnitude, so in this case we are on the right track. Okay, right, and that's how we'd answer that question. Now the last question, they say to us the barrier exerts an impulse of 14 Newton seconds to the left. Okay, so in this case, in that direction. Okay, so they say on the box, when the box strikes the barrier. Okay, now they say to us, calculate the change in kinetic energy of the box. Okay, after striking the barrier. All right, so in order for us to answer that question, in fact, yeah, I'm just going to continue over to this side if you don't mind. Okay, so I'm going to say, well, for 5.4, let's find out what the velocity is after colliding with the barrier. Okay, so I am going to simply say, I'm just going to use a different color, hope you don't mind. Okay, so I know the impulse there. Okay, they've already given me the impulse, but what is impulse? It's actually equal to the change in momentum, right? And keep in mind, we're going to have to keep in mind the direction in this case. One moment it was going that way, the other moment it's going the other direction. Okay, so I'm going to say, let's choose direction to the right as positive. Okay, that's going to be very, very, very important. Okay, so direction to the right is positive. So impulse, which is equal to, force multiplied by time, but we're not looking at force here, force multiplied by time, but in this case, this is also equal to the change in momentum, and that's the one that we're going to stick to. This is the impulse momentum equation. Okay, but they told us that that impulse is to the left. So in this case, it means that that impulse, because I've chosen right to be positive, that impulse would be minus 14 Newton seconds. Okay, and I'm going to say, well, that's equal to the change in momentum. So change in momentum, that's mass times change in velocity, right? So it's going to be my mass, that's 2, multiplied by final velocity, which is what we don't have. So this is the velocity just after it collides. So if we look at this as the, as our box, right, it was moving at 2 meters per, it collided 4 meters per second, positive 4, right? But then it experienced an impulse in that direction. So we don't know what the velocity is, over there. So this would be the final velocity, meaning the velocity, the speed after, after that collision, okay, which we don't know, minus the velocity initial. Now keep in mind, minus a positive 2. Okay, why do I keep saying 2? Minus a positive 4. So remember, when you talk about change in something, it's going to be final minus initial. So that's final minus initial velocity there, which was positive, right? Okay, and we can obviously do our gymnastics. So this is going to be minus 14 divided by 2, okay, which is minus 7, okay. So this would be minus 7 if I divide both sides by 2 there. That cancels that, and so VF minus 4. But I'm looking for final velocity. When I take this to the other side, it means that my final velocity, this is minus 7 plus 4, which would give us a positive 3 meters per second. A negative rather 3 meters per second. So in this case, that would be minus 3 meters per second. Okay, so it's telling us that after colliding with that barrier, the velocity of the box was actually in the negative direction that way. Okay, now remember, what did they ask us to find? The change in kinetic energy. Okay, so I'm going to say, well, the change in kinetic energy, that's EK final, EK final minus EK initial, right? We can actually just simplify it for ourselves and say half times the mass, okay, times VF squared minus VI squared, since half m is a common factor there. Okay, so that would be half of 2, okay, and yeah, that's basically 1. So that would be, now what's our final velocity? It's the velocity after collision. Now keep in mind, in this case, you're just going to put it in brackets. Even though it was minus 3, you can say minus 3 squared minus, in this case, your initial was 4. That's 4 squared. Okay, maybe let me do that. Put it in square brackets. Okay, and essentially that would be 9 minus 16, and that negative energy there. So your change in EK would actually be negative 7 joules. So I get negative 7 joules. Now remember that a change in kinetic energy, in this case, it means that that's the amount of energy, the reason why it's negative actually, that's the amount of energy that we lost during that collision there. You would imagine when you collide with that barrier there, there'd be a sound that comes out, all right? That sound actually means that it's energy that is lost, okay? Obviously there'd be a little bit of a distortion on the in the box. Some of the energy would have been used in doing that, and so that's why you've got negative 7 joules there of energy. Does not mean it's energy in the negative direction. Remember, energy is a scalar quantity. Okay, and just one last request from me to you, ladies and gents. Please, for those who who have brothers, sisters, cousins, anyone who might be going into grade 11, I would strongly advise that they start looking at the grade 12 content that is already available. I would actually say they better start working during the the holiday season, okay, so that they can actually hit the ground running going into grade 12. All right, and I'll see you guys next time when we discuss the next questions. Okay, sharp.